Hello. So this is Math 265, multivariable calculus. It's November 5th, 11:38ish. So let's see. Yesterday we finished up showing some examples how to integrate by first converting into spherical coordinates. So there is a more general theory of changing of variables, and I want to get to that. But to do that, it would be convenient if we first knew about something called the cross product. And the connection is not going to be clear at first with what I'm doing. So if you like, just take this as not connected to what we did yesterday, but just an extension of the work we did with vectors and the dot product. Okay? So it'll seem at first like we're backtracking a little bit. So today we want to talk about the cross product. So in physics class, have you guys seen the cross product yet?
I can't tell you. But I don't know. You need to show us.
You would know. You would know if you'd seen it. Okay. So here's the question. This is the motivating question. You start with two vectors, say A and B. We'll have their tails touch, say, at the origin. Doesn't matter so much. I want to find a third vector that is orthogonal to these vectors. Remember what orthogonal means. It means it's perpendicular to them, right? Or if you like, when you take the dot product, you get 0. So, well, graphically, it's kind of clear what I should do. I could just go up, right? And then that would be orthogonal to both of these vectors. These would have to make right angles. It's kind of silly looking square, but I think in perspective somehow that's what it should look like. Okay. Is there another option for this? I could go down. I could take the same vector and go down. So I have two different options for this. And in the end, we're going to choose one of these and call that the cross product. But for now, I won't tell you which. For now, we'll just try to solve the problem in a sort of naive way. So let me just, for the sake of argument, choose one of these and call that W, just so that we have a picture. Not that I'm really choosing that particular one. So if I give names to my coordinates here, A1, A2, A3, B1, B2, B3, and W will be W1, W2, X5. Didn't even finish it.
I heard that.
Okay. So A and B are given. And of course, we don't want them to be parallel to each other. If they're parallel going in the same direction, then there's just way too many of these things. We want them to really be going in different directions, so there's basically two possible ones. Okay. Now we want it to be orthogonal. This W, we want it to be orthogonal to A, and we want it to be orthogonal to B. So in terms of the dot product, it says that we want the dot product of A and W to be 0, and the dot product of B and W to be 0. That's what orthogonal meant. Okay. Well, we can compute this dot product, right? Just by looking at, we know how to do it. Just coordinate by coordinate, you multiply and add up, blah, blah, blah. So let's see. If A dot W is 0, then we get A1 W1 plus A2 W2 plus A3 W3 equals 0. And the same thing with the B's. B1 W1 plus B2 W2 plus B3W3 equals 0. So I have a system of two equations with three unknowns. Why? It looks like there's a lot more unknowns. It looks like there's 1, 2, 3, 4, 5, 6, 7, 9 unknowns. But remember, I'm given A and B. Somebody gives these to me. So all A1 through A3, B1 through B3, these are known. So the only unknowns are W1, W2, and W3. So I would like to try to solve this system. Now, it is always the case that if you have more variables than you have equations, then you shouldn't expect to get a unique answer. So there could be more than one. But if we can find one, we'll be very happy. Right? So let's just try to find at least one. All right, so the way I want to do this is I want to try to get rid of the W3. Right? So let's get rid of W3. So how am I going to do that? Well, I'm going to multiply this top equation, the whole thing, by B3. So that this last term will become A3, B3, W3. Now, why would I do that? Well, I'm going to multiply the bottom one by A3, so this becomes A3, B3, W3. So the last terms will be A3, B3, W3, A3, B3, W3. I'll subtract, and that whole W3 term will go away. I'm going to multiply here by B3, and I'm going to multiply here by A3. And then subtract. Okay, so this is a standard sort of method when you're trying to solve systems of equations. You multiply them by constants and then subtract one from the other to eliminate a variable. Okay, so if I do that, okay, I get A1 B3 W1 plus A2 B3 W2 plus A3 B3 W3. And then I get A3 B1 W1 plus A3 B2 W2 plus A3 B3 W3. And then I subtract. The third column dies. And what happens to the first two columns? Well, the first one, let's see, I get A1 B3 W1. And then this is A3 B1 W1. I can factor a W1 out of that. So minus A3 B1 W1. Okay, so that's what happens when I subtract these after multiplying. And then the second one, I get A2 B3 minus A3 B2. Notice the indices are just swapping. W2. And of course, these stay 0, so I get 0. Okay. Good, good, good. Whoa. Okay, so as I said before, you don't expect when you have more variables than you have equations. Now we're down to 2 variables in one equation to get a unique solution. In fact, in general, this should have infinitely many solutions to it. But we're happy with 1. So let's try to find 1. So let's see here. I want to multiply this thing by a W1 such that I get basically the opposite, right, the negative of what happens when I multiply this thing by W2. So let's see, here I have a B3 and a B3. That's an A1 and an A2, so it seems like I want to kind of multiply by what I'm missing somehow. Right? Here I'm missing the A2, and here I'm missing the A1. So I should try to multiply by here by A2 and here by A1. On the other hand, over here, you'll see the A3s are the same, but I'm missing a B2, and here I'm missing a B1. So in total, right, it looked like, let's see, I wanted an A2 for this one. Right, what else did I want? And I wanted a B2, right? Is that the... Oh, but I got to be careful. All right. Yeah. Okay, here's what I'm going to do. I'm going to throw in a B3, and we'll see why. Oh, actually, no, this is... I'm being so stupid here. I'm trying to do this micromanaging the whole thing. Now you just got to look at the big picture. All right, I'm going to take W1 and just let it be this thing. And I'm going to take W2 and let it be this thing, only I'll put a negative in front so that this becomes minus that. Yeah, I just swapped them. You look like you just stepped on a skunk. You're just like, right? So it's kind of like if you had, let's simplify this a little bit just to see what I'm doing. If you had 2x plus 3y equals 0, and you wanted to find an x and a y to do it, you let x be 3, and you let y be minus 2. Why minus 2 and not just 2? Well, if you do minus 2, then these will be the opposite of each other. Right? Because there's a plus here, so it really needs to be the negative of that. Okay, so I just take these coefficients and swap them, and one of them I put a minus in front. So I do the same thing here. I take this coefficient and I make that W2, but with a minus. I take this coefficient and make that my W1. Okay, so I just swap them. And of course, when I add these together, now I must get 0. Okay, so that's W1 and W2. We probably want to get W3 now. So how do we get W3? Well, we know that A3W3, I can solve for it. I just move these to the other side. So this is negative A1W1 minus A2W2. But I know what W1 and W2 are, so I can plug those into the formula. Okay, so this is negative A1 W1 is A2B3 minus A3B2 minus, minus A2 W2. And W2 has another minus, so let me put a plus. And this becomes A1B3 minus A3B1. And I don't like this minus here. So I'm going to put it inside. And to put it inside, I just have to swap these. So, and then, let's see, do I want to write it out? I can't remember if I want to write that out. Yeah, I do. Let's write this all out. So you get A1, A3B2 minus A1, A2B3 plus A1, A2B3 minus A2, A3B1. Now, do you see anything nice there? What's that?
A1, A2, B3 cancel.
Yeah, these two are the same, but one has a minus, one has a plus. So actually, those go away. You get A1, A3, B2 minus A2, A3, B1. Okay, so that's A3W3. So what does W3 equal?
A1, B2 minus A2, B1.
Yes. Divide by A3, right? A1, B2 minus A2, B1. Okay, that's nice because, okay, well I can rewrite my W2 as A3, B1 minus A1, B3. They're all now just, you take two of the A's and B's, multiply them, and then swap the indices and subtract. Okay, but we have found a solution. So W equals, okay, the W1 component is A2B3 minus A3B2. W2 is A3B1 minus A1B3. And then W3 is A1B2 minus A2B1. So we've actually found a vector that works. Good. Now we made a lot of choices. Yeah, when we chose this W1 and this W2, right, there were a lot of choices that we could have made for W1 and W2 that would have worked. But this is the one we made. And this is a cultural choice. I know we usually try to avoid those in this class, but we're going to make this cultural choice and we're going to stick with it. And we're going to give a name to this vector. Instead of calling it W, we're going to call this A cross B. This is not read times. Right? This is read A cross B. Or more glibly, A cross product B. So there's a formula. Now, think about the dot product formula. You did A1, B1 plus A2, B2 plus A3, B3. This is like that. Only instead of getting a number out, you're getting a vector. Right? This is really a vector again, not just a number. But again, it's gotten just by multiplying certain components and subtracting them in the right orders. Now, what's the problem with this formula? Think practically, as far as like taking a test. What's that?
Kind of difficult to remember.
Kind of difficult to remember. How are you going to remember this? I mean, there are three terms. Each one of them, okay, somehow it's not terrible, because if you remember the first term, the second term you get for free just by swapping. Okay, so that's not so bad. But you got to remember that it starts with A2B3 and then A3B1 and then A1B2. Well, it's not horrible, because if you think about a circle and you put the numbers 1, 2, and 3 on it, it's just kind of going around. It goes 2, 3, 3, 1, 1, 2. But why are you starting with 2? That makes it really hard to remember. Okay? But okay, so maybe you can remember that and you just think, okay, I go 2, 3, 3, 1, 1, 2. And I have to go around this way around the circle. Okay. Later we're going to show another way to remember it. Right? That doesn't require you to actually have to memorize this. Although it's not horrible to memorize that. You can break it down a little bit. Yeah. Okay. So this is the cross product. And the cross product is actually useful for answering some questions in physics and mathematics. It also has, because it's useful in physics, has a completely different definition. So remember when we defined the dot product, we did A1, B1 plus A2, B2 plus A3, B3, and then Kaiway said that's not how we did it in my physics class. In physics class, they defined it as A dot B is the norm of A times the norm of B times the cosine of the angle between them. And we proved that as a theorem. Okay? We're going to be able to do the same thing with the cross product. We're going to be able to write down, well, not actually for the vector itself, but at least for the norm of the vector, the size of A cross B. We're going to be able to write down a formula that is almost exactly the same. only you replace cosine with sine in the absolute values. Okay. Before we get there, let me ask you a simple question that we've already answered today, but that you should know. Which is, when are two vectors orthogonal? Right? That is, when is the angle between them 90 degrees? Well, what was the answer that we gave already today? If the dot product is 0. Right? So the answer is A dot B is 0. Okay, fine. Why? Why was that?
Because the cosine was.
Yeah, because, okay, if you have a 90-degree angle, then the cosine of 90 degrees is 0. Right? And of course, the formula for this is the norm of A times the norm of B times the cosine of theta, where that's the angle between them. And if this is pi over 2 or 90 degrees, this is 0. Okay, fine, that's if and only if. Okay, so what about this question then? When are two vectors parallel? Okay, so parallel means for vectors they're actually going in the same direction or opposite directions, right? Exactly opposite directions. Both would be considered parallel to us. We can use the same thinking, right? If they're going in the same direction, then the angle between them is 0. And so the cosine is 1. And if they're going in exact opposite directions, it's minus 1. So, and that's the only place where cosine is 1 or minus 1 between 0 and pi. So, they're parallel when the dot product is plus or minus the product of their norms. Right? Okay. They're going in the same direction if you get a plus. They're going in the opposite direction if you get a minus. So we're going to give a different criterion for parallel that looks a lot closer to the first one. Right? Namely, we're going to look at when something is 0 instead of a product of two norms. And that thing is going to be the cross product. Right? So it's going to be if the cross product of two vectors is 0, then they're parallel. Okay. So let's see how we do this. So the way we're going to do this is by computing something that we're not quite sure why we're computing it. Let's say I have two vectors, and I want to know what their norm is when I take the cross product. This is an important question. You take two vectors, you build another vector, A cross B. You should always know what the norm is. To make this a little bit easier, because we know that the norm involves taking a square root at the end, let me square it. That way I don't have to take a square root. At least if I do, I have to do it way at the end. I don't have to worry about that on my computations. So let me square this.
If the cross product you're doing for, if the vector only have x and y, doesn't have z, how the formula would be?
Great question. So the cross product is, this is the first time in this course that I have to say this, it is only defined for R3. This is the only thing really that we're doing in the course that just does not work. There's no analog in higher or lower dimensions. The cross product is very special. It's only used for three-dimensional vectors. Okay? This is very strange. This is why we have to live in 3 space. It's the only place you can do the cross product. Okay. So let's see. Well, to compute the norm of a vector, you have to square the components and then add them up. And then you take the square root, but we've got rid of that square root. Oops, that wasn't 2. So let's see. These are the components. We still have them written down. I have to square them and add them up. S-H-I-T. Okay, so this is A2B3 minus A3B2 squared plus, now let's see, I know I go 2 to 3, then 3 to 1. So A3B1 minus A1B3 squared plus, and then I go 1 to 2. So A1B2 minus A2B1 squared. Okay. So, there is a lot of algebra going on here, yeah? Okay. I don't think we should do this. So let me tell you what happened when I worked it out. So, if you like, you could write the words "and then a miracle occurs" in here, because we're not going to. You're not going to be able to see immediately why I'm going from this line to this. I'm just telling you, it's algebra. You just massage these equations, and it'll turn into what I'm writing. You have a problem with massaging? Yeah. Okay, so if you, I mean, this is like a homework problem. I give you two sides of the equation and say, show that these are the same. And so you start expanding and contracting, and all of a sudden you go, oh yeah, they're the same. Okay, there's nothing interesting going on here. It's just algebra. Okay. The nice thing about this form, and the reason why when I expanded this out, I knew to put it into this form, is because these things actually mean something. Right? What happened? What is it if you take a1 squared plus a2 squared plus a3 squared? What are you computing? The norm of a, almost the norm of a, but the norm of a squared, exactly, right? If there was a square root, it'd be exactly the norm of a. But there's no square root, so this must be the norm of a squared. And of course, this is the norm of b squared. Minus, now what is this guy? a1b1 plus a2b2 plus a3c3. That's the dot product. Sweet. So this is a dot b squared.
That's not a dot b in the first one, is it? This is just a.
Sorry, this is just meant to be a times, yeah. Those are numbers, so you certainly can't take the dot product. Well, you can. The dot product of two numbers is the same as the dot product of vectors of length 1, if you like. All multiplication of real numbers is a dot product, and it's kind of a stupid one, but true. Okay, now, a dot b, we have a formula for that. A dot b is norm of a, norm of b, cosine of theta. And then we square it so everything gets squared. So this is norm of a squared, norm of b squared, minus norm of a squared, norm of b squared, cosine squared, theta. Ah, this looks nice.
Wouldn't that be equal to norm of a squared, norm of b squared, sine of squared theta?
That's exactly right. If I factor out norm of a squared times norm of b squared, I get left with a 1 minus cosine squared. And 1 minus cosine squared is sine squared. So this is norm of a squared, norm of b squared, times sine squared theta. So, okay, this is a nice positive number. So if I take the square root of it, it just stays what it is. I don't need to worry about plus or minuses. I can put them all on one side anyway. When I square root all this, well, that's a nice positive number. That's a nice positive number. The only thing that might not have been positive is sine of theta. So when I take the square root of sine squared theta, I don't just get sine theta anymore. Right? Well, think if you did, then that could be negative potentially. And if that was negative, and these are positive, of course, then this would have to be negative, but it's a norm. It can't be negative. So when you take the square root of x squared, remember that it's not just x, it's absolute value of x. You should always get something positive out. So you have to put here absolute value of sine of theta. And, oh, that's not what I wrote in my notes. Which means... Oh, right, of course. So, okay, it's true what I wrote, but we can drop the absolute values. Why can we drop the absolute values? I claim sine of theta can't actually be negative. Well, when is sine of theta negative? Let's see. It starts at 0. Positive, 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 positive. Positive, 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 0. Has to be down here, right, when theta goes above pi. But you remember, what is theta? Theta is the angle between our two vectors. And we always assume that the angle between our two vectors is between 0 and pi. If it gets bigger, we just count it, we turn around and count it the other way. Right? We never let it get bigger than pi. So actually we can drop this. Since theta is between 0 and pi. So cool. This gives us a really nice formula for the length of the cross product. And it looks just like the formula for the dot product itself. Okay, and so the theorem that we can prove from this is that two vectors are parallel if, well, if they're parallel, that means that the angle between them is either 0 or pi. But whether it's 0 or pi, the sign is 0. Right? Sine of 0 is 0, sine of pi is 0. Right? So in either case, the norm of the cross product will be 0. In particular, the cross product has to be 0. Right? The only vector with norm 0 is 0. So two vectors are parallel if their cross product is 0. So they're orthogonal if their dot product is 0, and they're parallel if their cross product is 0. That fits nicely, I think. Nope. This is not so bad. Now there's another interpretation of this formula. It's quite nice. And that's in terms of the area of a parallelogram. So let's say I have a vector A, a vector B, and the angle between them is good old reliable theta. So as soon as I have two vectors going off in different directions, not say parallel to each other, I can make a parallelogram. I just stick this one at the end, and then drag it over. So I just copy B, copy A. And I get a nice parallelogram. And I'm curious what the area of this parallelogram is. So, generally speaking, the formula you always want to use when you have four-sided figures is somehow base times height. Well, you can take this A vector to be the base, but you can't take B to be the height because it's slanted. So what you have to do is you have to drop a right angle here. You drop an altitude. And that's actually your height right here. So the area equals the height times the base. And what's the base? It's the norm of A, right? The length of A. Okay, so what is the height? Well, one nice thing is we have a right triangle here. Nice right triangle, so we can use a little trigonometry on it. And let's see here. So, and we actually know the length of this hypotenuse, don't we? It's just the norm of B. So let's see, we know the opposite, and we know the hypotenuse, so that suggests we use sine. And so we know that, let's see, sine of theta is the opposite, h, over the hypotenuse, which is norm of B. And so h is equal to the norm of B times sine of theta. So my area equals, well, let's see, you have a norm of A times h, but h is the norm of B times sine of theta. It's just the norm of the cross product. That's really cool. You want to compute the parallelogram that's produced by two vectors, you just take their cross product and look at the norm. Now, this is really strange because remember how we defined the cross product in the first place? Is we took two vectors and said find a vector which is orthogonal to both. Somehow that process gave us a vector whose length is actually the area of this parallelogram. So this is kind of nice. It's actually going to give us a little bit more when we couple it with the dot product. And we're going to be able to compute the volume of a parallelepiped, which is the three-dimensional analog of a parallelogram. Let's see. Okay, we got that done. Good. Let me make just a quick remark. And this is really geared towards my 167, or 267 students. Yeah, we're in 267, all right. So if you don't know what I'm talking about, just feel free to ignore it. This is not something I'll test on or something. Don't worry about that. So the cross product is a binary operation. On the set of vectors in R3. Okay. Remember, a binary operation means you take two of them and you spit out a third. If you take two vectors, you can compute the cross product. Cool. But, well, when you first see a binary operation, you should start asking questions about how nice it is, right? Is it associative? Is it commutative? Does it have an identity? Does it, all these good questions, right? But this is a bad binary operation. Okay, now if you don't know what I've been talking about, you can start paying attention again, because this is important. Why is this a bad binary operation? Well, for instance, let's take two very easy vectors. Let's take the vector I and the vector k. So think what this is. You're taking, already went to 2 dimensions. Or, no, that's fine. So I goes out along the x-axis, k goes up this way. So this is your xz plane, right? So I goes out 1 unit, k goes up 1 unit. What do you suppose the cross product is? J is a good guess. Well, it's either J or negative J. How do we check? Well, we have a formula, right? And, well, we only really need to check the middle term of that formula. The first, if it's J, right, then it's 0, 1, 0. If it's minus J, then it's 0, minus 1, 0. So it's the middle term that we need to know. So let's just check the middle term. All right, let's see, it starts at 2, 3, so then it goes to 3, 1. So it must be A3, B1 minus A1, B3. Is that the middle term usually? Okay, and I is, let's see, 1, 0, 0, and K is 0, 0, 1. So let's see here. A3 is 0, so there's nothing there. And A1 is 1 and B3 is 1, but there's a minus. So it must be minus 1. So this is actually giving you minus J. This is, the cross product of these is going that way. I'm going to show you in a little bit a way to figure this out without having to think, without having to compute. But for now, yeah, that's the way it is. It actually turns out that this circle that I drew before, you can use that again. You do I, J, K. If you do I cross J, and you're going around the circle clockwise. If you do I cross J, you get K. Right? You just keep going around the circle. If you do J cross K, you get I. And if you do K cross I, you get J. But if you go backwards, like we did here, I cross K, you don't get J, you get minus J. So, where over here, I cross K is minus J, and all the rest of them are like that. So I cross K is minus J, but K cross I is J, which means that this is not a commutative binary operation. Right? So you can't just do it, you can't just switch the order. The dot product was not like that. The dot product, it didn't matter what order you did it in. Right? You always got the same answer. Cross product, it matters. Okay, so those of you in 267, you've seen a lot of examples where commutativity fails. So this isn't, earth-shattering news that there's a product that doesn't commute. But let me show you something that's a little more peculiar. Let's do I cross J. Okay, and so I have to tell you which I'm doing first. And the parentheses say that I'm going to do the I cross J first. Now let's see here. I cross J by the circle is K. So this is I cross K. And we just saw what I cross K is. It's minus J. Now let me just move the parentheses around. Make this I cross J. Now every time you've been in any math class and they move parentheses around, that didn't change things. But watch this. What's I cross I? Yeah, well, let's see. I and I are parallel to each other. It's the same vector. If two things are parallel, their cross product is 0. So this is 0 cross J. And this is, and mind you, this is not 0 the number. This is 0 the vector. It looks like 0, comma 0, comma 0. 0 cross J. You can do the cross product again. Of course, what are you going to get when you do 0 cross something? Well, there your intuition is right. It should be 0. And if you think about the formula, everything has to choose one of these numbers and then multiply by something, so it kills everything. So this is 0, which is definitely not minus J. So this cross product is such a bad binary operation, it's not even associative. I mean, you've never seen something like that before. So cross product is non-commutative and non-associative. In fact, if you look at that list of conditions that I gave you in 267, divisibility, identities, inverses, not one darn thing holds. But the only nice thing is that 0, kills anything. That's about it. At least as far as the typical structural properties we want to hold. But it's not completely horrible. There are some properties that hold, and these are worth knowing. Okay? And the proof is just by breaking down the formula. Right? It's just, they're all just verifications, so we won't do them. They're not terribly interesting. Okay, so the first one is what we just said, which is that if you take the cross product with 0, from any direction, you get 0. Now the second one says, well, if you switch the order, we already saw that you don't get the same thing out. In all our examples, what happens is actually we get to minus n. And that actually is always going to be the case. So it will be minus b cross a. So you can spin them around, but you always pick up negatives. Sometimes this is called anti-commutative. The next one is quite nice. It's somehow a linearity property. It says that if I multiply my vector by a constant, so here C is not a vector, this is just a number. So if I multiply A by C, and then take the cross product, this is the same thing as if I had first multiplied B by C and taken the cross product. And this is actually the same thing as if I had taken the cross product in the first place of just A and B, and whatever my answer was, I multiplied by C. So you can pull constants in and out. You can put them wherever you like to. Let's see. Right? Yeah. The next one is a distributivity condition. And it just says that it actually works the way you want it to. Right? This is A cross B plus A cross C. So distributivity actually does work. And it actually works on both sides. So if you have A plus B, and you cross product with C, this is A cross C plus B. And of course, you can prove that using the number 2, the anti-commutativity law, and number 4. Okay, so 6 is a really interesting one because it's going to relate the dot product with the cross product. And this is sometimes called, what's it called? The scalar triple product. Kind of an impressive sounding name. So it says the following. First, take B and C and take the cross product. So that gives you a new vector. Now take A and do the dot product. So this is a vector with a vector. It gives you a number. And this turns out to be the same thing as if you first took the cross product of A and B and then did the dot product with C. So you can swap. If you have a dot product and then a cross product, right? Well, really I should say you have a cross product and then you do a dot product on one side, you can swap the cross product and the dot product and you get the same number out. Right? And still, this is a vector, cross of a dot product with a vector, so this is really a number. Okay? And the last one is a formula for what happens if you take, well, it's exactly what we were looking at on the left side. It's the associativity condition that we don't have. So what do we have instead of associativity? So instead of associativity, you get the following. You take the dot product of A and C, so that gives you a number, and you multiply this times B. So B is a vector, you have a number times a vector, so this is a vector. Then you do the same thing again, but you swap the roles of B and C. So A stays fixed, but now you're going to swap B and C. So now you do A dot B and multiply it by the vector C, and you're going to subtract in between. Okay, so you end up with a vector minus a vector, which is a vector, and that's good because on the left you have a vector. So let's test if that associativity condition works for the stuff we did over here. So here we had I cross J. So we already computed this. It ended up being minus J. Okay, so let's compute the other side. So the other side would read I dot J times I minus I dot I times J. So let's see, what's I dot J? So these are vectors that are orthogonal to each other, right? What happens when you dot product orthogonal vectors? You get 0. So this whole thing is 0. And then what happens if you dot product I with itself? 1, 0, 0, dot 1, 0, 0. So it's just 1 times 1 plus 0 times 0 plus 0 times 0. So it's 1. So that's 1 times J. So you have minus 1 times J is minus J. Okay, sure. Look, it worked. This was 0. And this is 1. Okay. Cool. At least for one formula that, or for one example, that formula that holds. But you can prove it, right? You just have to, the way to do it is you break all of these things down into their component parts and say, okay, how do I take the cross product of these two vectors? I write down a formula, then I take another cross product with this formula, and then I do dot products on the right side. And you just look, and you say, oh, look at that, the formulas are the same. Okay, cool. So it works. Okay. Let me give you the rule for how to tell which direction the cross product is going to point. So you maybe have heard it in physics. It's called the right-hand rule. Or in physics, sometimes they have the left-hand rule. I've seen this before, but no, we use the right-hand rule for the cross product here. The right-hand rule. So if you, make sure I draw this in a good way. Draw it like this. What's the problem? You were laughing at the rule?
No, I'm trying to verify that the left-hand rule is actually...
Oh, you're looking up online to see if there is a left-hand rule?
No. Just forget it.
Okay. So let me switch these for the purposes of my diagram. Okay. Okay, so you'll notice here I have an arrow pointing which direction I'm going. Okay, and the way I know which direction I'm going is the way I write it. I write A cross B. If I wrote B cross A, the arrow would be going from B to A. Okay, so that's how you know which way to point the arrow, is which comes first. Okay, and here's what you do. You take your right hand. Does everybody know the right hand? It's important because if you're on a test and you do this with your left hand, you'll get the negative of the answer. So right hand. Yeah. If you hold up your left hand like this, you'll see it makes an L. That's your left hand, see? L left. But your right hand doesn't do that. It makes a backwards L. Okay. So you take your hand, your right hand, and you point the fingers in the direction of the arrow, right? You point them towards the second vector. And then stick your thumb up. And where your thumb points, that's the direction of the cross product. Right? If we were going backwards, if we were doing B cross A, then what would you have to do? Well, now to get your, there we go, turn this way. Now to get your fingers pointed in the right direction, towards it, the thumb has to point down. So it's going in the down. And of course, that's what should happen, right? If you switch the order, it negates the vector, right? So if you're going backwards, then the vector has to go down. So for A cross B, it goes up. And for B cross A, it goes down. So it's actually kind of fun to try to use the right-hand rule on this to see which direction things are pointing. Don't do it in class. Do it like when you're on the bus. Because you'll be sitting there going, and people are just going to freak out. And, what are you doing? I'm doing calculus. I'm doing calculus. Thank you. Thank you very much. Okay. So let me show you this one trick that I promised with the volume of a parallelepiped. So it's very similar sort of derivation as the one that I'm erasing right now. In fact, maybe I can salvage the picture. Can I salvage my picture though? It's probably better if I don't. Yeah, it's probably better if I don't. Alright, so since this is going to be a parallelepiped, which is a three-dimensional parallelogram, I need three vectors, A, B, and C. So let's see. So I got an A going somewhere. I got a B going somewhere, and then I have a C going like back into the board. So I have like an A, a B, and a C. And so what I can do is I can turn this into a parallelepiped. So how do I do that? So I connect everything up. Where's that going to stop that? I guess you can't really see that. It should be dotted, shouldn't it? There we go. All right. That's going. We'll go back a little. We'll go back a little. That's the C vector that I'm copying. Okay, that's roughly a parallelepiped. Oh. Okay, I swap my. Let me swap my A and B just so I'm consistent with my notation. My note doesn't change anything, of course. Okay, and we want to compute the volume of this thing. Well, just like when we computed the area, you take the length of the base times the height. For the volume, you take the area of the base times the height. So to get the area of the base, well, there's a base, and now I need a height. So the height, if you like, can go out this way. You drop a line. There's a nice right angle. And let's see which angle. I think I took this one. We'll call that angle theta, and this height we'll call h. And then the base here, I'll call that A. So the volume is equal to the area of the base, which is A, times the height. Okay, so we just need to compute those things. So let's see. So A, well, that's just the area of a parallelogram. We know how to compute that now. The area of a parallelogram that's given by two vectors, B and C, is just the norm of the cross product. So A is just the norm of B cross C. Okay. Now what about the height? Well, the height I should be able to get just... oh, this is going up too high. That's the height right there, right? There we go. This is still vector A. That's the height. Okay. This we should be able to just get using trigonometry. Because, well, we're looking for h, which is, the adjacent side, and we have the hypotenuse. It's just the norm of A. So, the cosine of theta is the adjacent over the hypotenuse, which is the norm of A. And so h is equal to the norm of A times cosine of theta. And so the volume equals the norm of A times the norm of B cross C times cosine of theta. Keep this. But this formula should look familiar. Right? This formula is what happens if you take the dot product of A with B cross C. Right? How do you do the dot product of A and B? It's norm of A, norm of B times cosine of theta. Norm of A times norm of B, well now it's B cross C, times cosine of theta. Well, what's the theta? Theta is supposed to be the angle between them. Right? But sure enough, right? Theta is the angle, right, between this vector and A. And what is this vector? Well, it's a vector which is orthogonal to B and C. It's exactly the cross product. So this we can write actually as A dot B cross C. Okay, but here there's a little quirk. This theta, between 0 and pi over 2, cosine is positive, but between pi over 2 and pi, it does become negative. And all we know for sure is that theta is between 0 and pi. So this thing could become negative, in which case that's bad because volume is supposed to be positive. So the way we correct that is by putting absolute values around it. Okay. So the volume is given by this A dot B cross C, which looks exactly like what's in number 6, because it is. Right? This is what I was calling the scalar triple product. So if you have a parallelepiped given by vectors A, B, and C, then the volume of that parallelepiped is just given by the norm of the scalar triple product. So this is quite nice. You didn't need a triple integral to compute it. So it's already quite good. Okay, so work on your homework on more on your triple integrals over the weekend. Next week, the first thing we'll do is learn how to compute the cross product in a slightly more efficient way using determinants of matrices instead of having to remember this formula. And determinant, and the reason why I do that is, well, some of you might actually think it's harder to use determinants of matrices, but we're going to need matrices and determinants all over the place. So we can talk about Jacobians, for instance. And Jacobians has nothing to do with the French revolutionary political group or anything. In case you were wondering.
Next Tuesday. So the next time